The nominal trajectory of interstellar asteroid A2017U1, as computed based on the observations of October 19, 2017 and thereafter. Note the differing orbits of the planets: fast and circular, the Kuiper belt objects elliptical and roughly coplanar, and this interstellar asteroid. Image credit Tony 873004 of Wikimedia Commons. When you look at how the planets orbit in our solar system, the correct answer was given hundreds of years ago, first by Kepler, whose laws of motion described it, and then by Newton, whose law of universal gravitation allowed it to be derived. But comets, both the ones originating from our solar system and the ones coming from far beyond it, don't move in those same, nearly circular ellipses at all. Why is that? Rajasekar and Rajagopalan wants to know. Feeder comets orbit the Sun in a parabolic path, unlike planets which orbit in an elliptical one. Where do comets get the energy to travel such a long distance, from the Oort cloud to the Sun back? Also, how could interstellar comets asteroids come out of their parent star system and visit other ones? We can answer this, but there's an even bigger question we can answer: why do all objects orbit the way they do? The planets of the solar system, along with the asteroids in the asteroid belt, orbit all in almost the same plane, making elliptical, nearly circular orbits. Beyond Neptune, things get progressively less reliable. Image credit Space Telescope Science Institute, Graphics Department. In our solar system, we have the four inner, rocky worlds, an asteroid belt beyond that, gas giant worlds with this slew of moons and rings, and then the Kuiper belt. Beyond the Kuiper belt, we have a large, scattered disk, which gives way to a spherical Oort cloud, extending a tremendous distance, perhaps 1 or 2 light-years away, almost halfway to the next star. A logarithmic view of our solar system, extending out all the way to the next nearest stars, shows the extent of the asteroid belt, Kuiper belt, and Oort cloud. Image credit NASA. In order to be in a stable orbit at a certain distance, according to the laws of gravity, each object needs to be moving with a particular speed. In terms of basic physics, there needs to be a balance between the potential energy of the system in the form of gravitational potential energy and the energy of motion kinetic energy. When you're deeper in the Sun's gravitational potential well, meaning when you're closer to the Sun itself, you have less energy overall, and you need to move faster to have a stable orbit. 8 planets of our solar system and our Sun, to scale in size but not in terms of orbital distances. Mercury is the most difficult naked eye planet to see. Image credit Wikimedia Commons user WP. This is why, if we look at the average speeds of the planets in their orbits, they are Mercury 48 km/s, Venus 35 km/s, Earth 30 km/s, Mars 24 km/s, Jupiter 13 km/s, Saturn 9.7 km/s, Uranus 6.8 km/s, Neptune 5.4 km/s. Because of the environment in which the solar system formed, of tiny masses that then merged together, interacted, and caused many ejections, what's left over today is pretty close to circular. The orbits of the planets in the inner solar system aren't exactly circular, but they're quite close, with Mercury and Mars having the biggest departures. Additionally, the closer in a planet is to the Sun, the greater its speed must be. Image credit NASA JPL, but there are also gravitational interactions that occurred later times to consider. If an asteroid or a Kuiper belt object passes close to a large mass, like Jupiter and Neptune, it can have a gravitational interaction that gives it a kick. This will change its velocity by a substantial amount, up to a few kms in pretty much any direction. For an asteroid, that can cause its orbit to go from roughly circular to highly elliptical. The path of Comet Encke, which may have had its origin in the asteroid belt, is a good example of this. The trail of Comet Encke, which makes a complete orbit every 3.3 years, is extremely short period but spread out in an eccentric ellipse that traces the comet's orbital path. Encke was the second periodic comet identified after Halley's Comet. Image credit Gez, R.D., Reach, W.T., Woodward, C.E., and Kelly, M. S. 2006. On the other hand, when you're very far out, like in the Kuiper belt of the Oort cloud, you might only move at a speed of 4 km/s for the inner Kuiper belt down to just a few hundred meters for the Oort cloud. A gravitational interaction with a major planet, like Neptune, could change your orbit in one of two directions. If Neptune steals energy from you, it will kick you into the inner solar system, creating a long-period ellipse, similar to comet Swift-Tuttle, the comet that created the Perseid meteor shower. This would be an ellipse that's barely gravitationally bound to the Sun, but that's an ellipse nonetheless. The orbital path of comet Swift-Tuttle, which passes perilously close to crossing Earth's actual path around the Sun, is highly elliptical compared to any planetary orbit. It's conjectured that a long argo-gravitational interaction with either Neptune or another massive object altered its orbit to match what we see at present. Image credit Howard of Teaching Stars. But if Neptune, or any other body we still don't know most of what's out there in the outer solar system gives you extra kinetic energy, it could change your orbit from a bound, elliptical orbit, to an unbound, hyperbolic one. Parabolic, by the way, is an unbound orbit that's exactly on the border between elliptical and hyperbolic. For those of you who remember the sun-grazing comet Ison from 2013, which disintegrated when it came close to the Sun, it was on a hyperbolic orbit. Typically, comets originating from the outer solar system will be within just a few kms of the border between bound and unbound. As comet Ison passed into the inner solar system, it developed a set of tails that pointed almost directly away from the Sun. It grazed the Sun at a distance of less than 2 million kilometers, and disintegrated thereafter from its close approach. Image credit Adam Blockmount, Lemon Sky Center, University of Arizona. The oddest fact about comets that's counterintuitive to most people is that they don't need a lot of energy to plunge into the inner solar system. If I had a mass at rest relative to the Sun, even a light year away, and just let it go, it would fall straight into the Sun if we waited long enough. For orbiting distant masses in our solar system, a very small change to its velocity can nudge it close to this orbit. While these gravitational nudges from nearby objects happen in more or less random directions, we only see the objects that start moving fast and come close to the Sun, developing tails and becoming bright enough to be seen. This is where comets come from. The Kuiper belt is the location of the greatest number of known objects in the solar system, but the Oort cloud, fainter and more distant, not only contains many more, but is more likely to be perturbed by a passing mass like another star. Note that all Kuiper belt and Oort cloud objects move at extremely small speeds relative to the Sun. Image credit NASA and William Crocco. The vast majority are either barely gravitationally bound or barely gravitationally unbound, which is why A2017U1 was such a tremendous discovery. Unlike every other comet or asteroid we've ever seen, it was extremely unbound. While objects from our outer solar system move, once they're far from the Sun, at just a few kms tops, this one was moving at more than 20 kms. It must have come from outside the solar system, as even Neptune wouldn't have enough mass and speed to impart that kind of velocity to it. A 2017 U1 is most likely of interstellar origin. Approaching from above, it was closest to the Sun on Sept. 9 traveling at 27 miles per second, 44 kilometers per second. The comet is headed away from the Earth and Sun on its way out of the solar system. Image credit NASA JPL Caltech. The secrets of what makes a comet, asteroid, or an object beyond our solar system orbit the way it does. It's simply gravity, and the gravitational interactions throughout its history. Objects stably in our solar system, particularly after 4.5 billion years, are all moving in elliptical orbits around the Sun. But gravitational interactions can change that, either changing the shape of your ellipse or transforming it into a barely unbound hyperbola. In either case, we'll only see it if it gets slingshotted close to the Sun, which is the only way we know about all the comets we've ever discovered. The tails of comets do not follow the orbital trajectory exactly, but rather make either straight or curved paths away from the Sun, depending on whether it's ions or dust grains that get blown off. In any case, comets are only visible, with tails, comas, and the reflectivity of sunlight, when they're close enough to the Sun. Image credit Wikimedia Commons user Roger Dimmick. The comets and asteroids that get ejected from our solar system fly through interstellar space, where they will someday pass near other stars. Since the stars move through the galaxy at relative speeds of around 10 to 30 kms, that's how fast these interstellar space rocks are likely to move, explaining why the interstellar asteroid we discovered was moving so quickly. It's just a combination of initial orbits, gravitational interactions, and the motion of our solar system through the galaxy that explains it all. When you steal energy from an object in the asteroid belt, Kuiper belt, or Oort cloud, you create an ellipse that's more tightly bound to the Sun. But when you give it an energetic kick, it just might be enough to eject it altogether. Although we now believe we understand how the Sun in our solar system formed, this early view is an illustration only. When it comes to what we see today, all we have left are the survivors. Image credit Johns Hopkins University Applied Physics Laboratory Southwest Research Institute Durrell 3. The big lesson from this: our solar system is continuously depopulating over time, and has fewer objects in its asteroid belt, Kuiper belt, and Oort cloud than ever before. As time goes on, they all get sparser and sparser. Who knows how many were once present? It's an impossible task. In the solar system, all we'll ever have access to are the survivors.